Uh, Another example is this. Find the Taylor series for cosine x about x equals pi over 3. So this means find the Taylor series of cosine x in powers of x minus pi over 3. Now cosine x is just this expression, right? Minus 1 to the power n, x to the power 2n divided by 2n factorial. You should keep in mind the series expansions of three functions: e to the power x, sine x, and cosine x. Okay, and of course, 1 minus x and so on. But it's good to know these examples. Okay. Bu da deminkine benzer bir şey. Hani kosinüsün pi bölü 3 civarındaki açılımını soruyor. Kosinüs x'in bu olduğunu biliyoruz. Cosine x can be written like this. Cosine x minus pi over 3 plus pi over 3, right? And this is just uh, cosine x minus pi over 3 cosine pi over 3 minus sine x minus pi over 3 sine pi over 3. So this implies cosine x is just cosine pi over 3 1 over 2, right? 1 over 2 times cosine x minus pi over 3 minus sine pi over 3 sinüs 60 kök 3 bölü 2, right? Sine x minus pi over 3. And so I need also this gadget. This was just this. And finally, I'll just write these from these formulas. Instead of x, I will write x minus pi over 3 here and here. So we get what? 1 over 2 times cosine x minus pi over 3. This is 0 to infinite minus 1 to the power n. X minus pi over 3 to the power 2n divided by 2n factorial minus square root of 3 over 2 and then summation sine pi over 3 minus 1 to the power n. Instead of x, I write x minus pi over 3 2n plus 1 divided by 2n plus 1 factorial. Okay, that's it. And what is the radius of convergence? Radius of convergence for both sine and cosine were infinite. So it is still infinite, okay? This is true for all x in R. So to get the Taylor expansions of functions at near some point other than 0, you have to play with the function, okay? You have to, there is no, straightforward way of obtaining the power series. Sometimes you take derivative or sometimes you play tricks like this, okay? One final thing about Taylor expansions is the following. Taylor's formula. I guess you have seen Taylor's formula in 119, right? Remainder formula for uh, Taylor expansion. 119'da. Yeah, I think you have seen that. Sorry. Okay, okay. No, you see, I am asked to find Taylor expansion of cosine x about pi over 3. So I write cosine x like this, and then I have this expansion for this gadget. It has both sine and cosine terms in it. And then for this one, I need cosine series. For this one, I need sine series. Okay. Well, Taylor's formula is this theorem. If the n plus first derivative of f exists on an interval containing c and x, and if p and x is the Taylor, okay, so p and x is this. If p and x, so this is f of 0 plus, no, f of c plus f prime c divided by 1 factorial x minus c, up to you go this. So you take actually the Taylor series up to nth term. This is called Taylor polynomial. Is the Taylor polynomial of f of x about x equals c, then f of x is equal to Pn of x plus En of x holds, where Enx is given by either of the following formulas. So Pn of f of x is approximated by this polynomial, Taylor polynomial, and the error term. So the actual value minus the approximation is the error term, and error term corresponding to this nth polynomial approximation. And the formula for En of x is the following. There are two formulas for this. One of them is called Lagrange Remainder. Possibly it is due to Lagrange. So Lagrange tells us that this is equal to n plus first derivative of the function evaluated at some point divided by n plus 1 factorial x minus c to the power n plus 1 for some s between c and x. So it's like this. Here this is c, okay, and so this is where you take your Taylor expansion, and this is your x, and Lagrange remainder says that there is some s here. You don't know what the value of s is, but it is between c and x, so that this error term is equal to this expression. Okay. There is another formula for this. That is called the integral remainder. So the same thing is also equal to the following. En of x is 1 over n factorial integral from c to x, x minus t to the power n plus first derivative of f at t dt. Now you integrate this function with respect to t, x minus t to the power n, and then you have this. Okay, this is called integral remainder. Here, uh, you know, you don't have any extra s value. Okay, this tells us there is some s, so that this is equal to this gadget. This is maybe more straightforward. You just integrate this expression from c to x. Okay. We can use Taylor's theorem to, for example, prove that e to the power x or sine x has the... Yukarı mı çıkayım? Bir tane örnek yapayım bu nasıl kullanılıyor diye. Okay. Let's show that sine x equals its Taylor expansion. Yani şunu göstermek istiyorum. We want to show this. This is equal to n from 0 to infinity minus 1 to the power n over n factorial x to the power 2n plus 1. Okay. For this, I'll do the following. So let f of x equals sine x. Okay. Pn of x is the nth Taylor polynomial. So it is just this gadget. K from 0 to n minus 1 to the power k factorial x to the power 2k plus 1. So it is the following. X minus x cubed over 3 factorial x to the 5 over 5 factorial x to the power 7 over factorial and so on up to nth term. Nth term. Okay. Well, then the theorem tells us that f of x minus p(n) of x is equal to en of x. And what is this? Okay. Where theorem tells us that en of x is equal to the following. N plus first derivative of f at some point divided by n plus 1 factorial and then x minus c to the power n plus 1. Here I take c equals 0, right? We look at Maclaurin series. So the error term is just n plus first derivative at s n plus 1 factorial x to the power n plus 1. And what is s? For some s between 0 and x. Okay, now what is this error term? En of x. En of x in absolute value is the is this expression, right? Now, what is this derivative term? F is sine x. So any derivative of this is either sine or cosine, right? Sine x, cosine, it sometimes minus cosine, sometimes minus sine. But this derivative is either sine x or cosine x. In absolute value, this is less than 1, right? So any derivative of this, is either sine plus minus sine x or cosine x. So when you take the absolute value, it is less than 1, right? So this fn plus first derivative of this is less than 1 because it is either sine or cosine. So this means what? I can just replace this term by 1. Okay, I'll get something bigger, n plus 1 factorial, and then absolute value of x to the power 1. But you see, x is a fixed number, right? So you have x to the power, x could be anything. X could be 1 million, but then this will be, 1 million to the power 6, or 6, so n plus 1 will be just 10 times, okay, this very big number, but in the denominator you have n plus 1 factorial. Factorial grows much faster than any power. Okay, so this thing goes to 0 as n goes to infinity. This means what? En of x goes to 0, right, in absolute value. So the error term goes to 0. This means I had this sine x was Pn of x plus En of x, and what we know is that this term goes to 0 as n goes to infinity. So sine x is equal to limit Pn of x as n goes to infinity, because the error term goes to 0. Right? Bu sıfıra gidiyorsa Pn of x sin x'e eşit olacak. Right? Yani şöyle En of x, but this is just 0. So I have limit as n goes to infinity Pn of x. So what is this Pn of x? It is just the following. Limit as n goes to infinity, summation from 0 to n minus 1 to the power k, x to the power 2k plus 1 divided by 2k plus 1 factorial. So if I let n go to infinity, this is just 0 to infinite. Tamam mı? Dolayısıyla da sin x gerçekten buna eşit. So sin x is really equal to its Taylor series. In the previous hour, I said this as a fact, but I didn't prove it. Now we can prove it, but of course we are using a big machinery. We are using Taylor's theorem, okay? So it's not, without Taylor's theorem, this is difficult. This is true for all x in R. Tamam mı? Şey de yapabiliriz. Hemen ona da geçelim. Using this series, when they are alternating, we can use alternating the error estimate for the alternating series to approximate these functions numerically. So that's the next section, 9.7, applications of Taylor and Maclaurin series. Şu yüzden I want to show that sin x is equal to this gadget, okay? If you take first n terms of this infinite series, that's called Taylor's polynomial, okay? Taylor's polynomial, yeah, in the theorem. And I want to show that actually the function is equal to this Taylor polynomial when n goes to infinity. So the whole Taylor series, okay? And to show that, since I am given this by the theorem, I want to show that as n goes to infinity, Pn of x is equal to f of x. That's the same thing as saying that En of x goes to 0. Değil mi? Let's do some examples. Compute cosine 43 degrees with error less than 1 over 10,000. Okay, 10,000. Let's see how we can do this. Okay. Now, cosine 43 degrees is just, I want to write everything in, of course, radians. So this is 43 pi over 180 radians. And what was the Taylor's formula for cosine x? It was this: 1 minus x squared over 2 factorial, x to the 4 over 4 factorial, x to the 6 over 6 factorial, and so on. As I said at the beginning of the hour, you should keep in mind Taylor series of exponential function, sine x and cosine x, okay? Always. Cosine x is this. So I'll just plug this gadget in the formula. So we have 1 minus 43 pi over 180 squared, well, 1 over 2 factorial plus 1 over 4 factorial, 43 pi over 180 cube, no, fourth power, and then 1 over 6 factorial, and so on, okay? This is till infinity. I want to know where should I cut this so that the error will be less than 1 over 10,000. You see, this is an alternating series, right? This is like A0 plus A1 plus A2 plus A3 plus AN. And this is which is an alternating series, which is an alternating series. series. So if S is this, okay, this summation, if Sn is just the sum of the first n terms, let's say, up to an, then we know what? We know that S minus Sn is less than an plus 1, right? N plus first term. So I need to choose this guy less than 1 over 10,000. So hence we need to choose find n so that n plus 1, an plus 1 is less than 1 over 10,000. What is an plus 1? An is, so this is a0, a0, a1, and so on, right? An is this. an an şu eksi 1 üzeri n eksi 1 değil mi? A1 an n'inci terimde 2n faktöriyel, ondan sonra da ne var? 43 pi bölü 180 üzeri 2n. Bakalım tutuyor mu? Şimdi 0 koyarsam a0 is just no, a0 şu olmalı. A0 pozitif 1 over 1, so a0 is 1. Yes. What is a1? A1 is minus 1 over 2 factorial 43 pi over 180 squared. Öyle mi? Evet. A2 da 1 bölü 4 faktöriyel olacak. A2 is just 4 factorial to the power 4. Yes. So this is correct. Peki o zaman yani A1 işte eksi 1 bölü 2 43 pi bölü 180 üzeri 2 ne? Peki an plus 1 ne? An plus 1 minus 1 to the power n plus 1 2n plus 2 factorial 43 pi over 180 2n plus 2 değil mi? Ne yerine? I write n plus 1 for n. I want this to be less than 10,000. An plus 1 less than 1 over 10,000 means what? Absolute value of this number 43 pi over 180 2n plus 1 no 2 less than 1 over 10,000. This is same thing as saying 2n plus 1 no 2n plus 2 factorial times 180 divided by 43 pi to the power 2n plus 2 larger than 10,000. And bakayım bunun için ne bulunmuş? Ne eşittir 4 oluyormuş. So n equals 4 works. Yani n yerine 4 yazarsanız if you write 4 you get 10 factorial and 10th power of this. So this is less than in this case this expression. So it is just 10 factorial 180 over 43 pi to the power 10. This is 40,300 and this larger than this. So it means you need to choose n 4. Bu da ne demek? Sıfırdan 4'e kadar alacağız. So cosine 43 degrees is approximately I just need to write 4 terms. Yani ne yapacağım? Evet. 1 neye eşittir? 4'e kadar gideceğim. 1, 2, 3, 4. Yani şöyle yazayım ben ne çıktığını. 1 minus 1 over 2 43. Sorry? Well, I mean, no, but we will, if we ask anything like this, it will be something easy to compute, okay? Not like this. And then 6 factorial 4 to 3 pi over 180 to the power 6 plus 1 over 8 factorial 4 to 3 pi over 180 to the power 8. So with error less than 1 over 10,000. Indeed, computers, calculators all use this power series expansions to compute functions like exponentials, trigonometric functions, logarithms. Okay, so this is how actually computers compute these functions. They use Taylor expansions. Okay. So this is one application of Taylor series. You can approximate functions if the Taylor series is an alternating series. Okay, then it's very easy. Another application of this functions defined by integrals. Okay, consider this function. This is an important function in mathematics and in engineering, I guess, statistics and so on. E to the power t squared, right? This is like Gaussian distribution function. It is, of course, from minus infinity to it goes from minus infinity to x, but this is something similar to that. So this is an important function, but you cannot compute this integral directly, right? You don't know what the antiderivative of this. However, using Taylor series, you can compute this integral as a power series. How? Well, e to the power x is just, or e to the power t is just what? T to the power n over n factorial, and from 0 to infinity. Therefore, e to the power, and this is true for all t in R. So, e to the power minus t squared is what? Minus 1 to the power n e to the power tn divided by n factorial. And this is again true for all t, right? I plug minus t squared for t. So minus 1 goes out as minus 1 to the power n, and t squared to the power n is just t to the power 2n divided by n factorial. Well, then I have what? My ex is defined as the integral from 0 to x e to the power this function. Well, you just integrate this expression and from 0 to infinity. And we have seen last time that yesterday, if you have a convergent series, which is convergent, this is convergent for all t. Therefore, I can just integrate it term-wise. So this is just, okay, this is a theorem. I can just integrate this gadget like this. So this is just minus 1 to the power n and factorial integral of this 2n plus 1 divided by 2n plus 1, and you need to compute this at 0 and x. All right, what else? This is just 0 to infinity minus 1 to the power n 2n plus 1 times n factorial, and then you plug x here, so x to the power 2n plus 1 minus 0. When you plug 0, you just get 0. So that's it. So exponential, this function ex, we don't know this function in terms of elementary functions, but it is this is the best thing you may have. It is just this power series. It is the function given by this power series. As I said, most of the functions doesn't have a name. Okay, the functions we encountered so far are elementary functions. They are polynomials, rational functions, logarithms, sine, cosine, exponentials, and so on. But they are just uh, very few among all the functions. So this function cannot be written, for example, in terms of elementary functions. The only way you can represent this is this power series. Okay, it doesn't have a name other than this. Yani dediğim gibi fonksiyonların çoğu elementary fonksiyonlar cinsinden ifade edilemezler. Onlar çok az bir yer tutuyor elementary fonksiyonlar. Geri kalan bütün fonksiyonlar için yapabileceğiniz en iyi şey onların e, analitik olduğunu umacaksınız ve Taylor seri expansion'ları olacak. Bunun gibi. Bir de tabii analitik olmayan da dünya kadar var. Alright. We can also use Taylor series to compute limits. Let me also mention that. Another example. Computing limits using Taylor series. How? Let's, for example, compute this limit. Of course, we can compute this limit without using Taylor series, right? This is 0 over 0. So you need to apply L'Hopital's rule several times. You can obtain the limit. But we can also do the following. You see, sine x is what? Sine x is this. X minus x cubed over 3 factorial, x to the 5 over 5 factorial, x to the 7 over 7 factorial, and so on, right? It goes like this. And everything is divided by x cubed. So this is equal to what? Limit as x goes to infinity. When you subtract this, X will disappear. X terms will disappear. So this is cancelled with this one. And then you see the first term starts with x cubed and you divide by x cubed. So you make the cancellation over there also. So minus minus becomes plus. This is plus x cubed over 3 factorial. So this is just 1 over 3 factorial. X cubed divided by x cubed. So you have this. And then you have minus x squared over 5 factorial plus x to the 4 divided by 7 factorial plus x to the power 7. I have no 9 olacak. 9'u 3'e böldük 6. 9 factorial, right? Bunlar 3, 5, 7 diye gidiyor. Goes like this. And you let x go to 0. When x goes to 0, this is a convergent power series. It defines a continuous function. Therefore, you can just substitute x equals 0 in this power series. So this is just 1 over 3 factorial minus 0 plus 0 minus 0 and so on. So this is just 1 over 3 factorial. Here I am using the fact that, since this is a convergent power series, it defines a continuous function, okay? So that when you take limit, you just plug the value. Okay, so these are some possible applications of Taylor series. Any questions so far? Okay, now we have finished all the material in chapter 9. I have 1 hour left. In the last hour, I can answer your questions. I mean, if you have any questions, I can do a recitation hour. Okay? Bunu da öyle yapalım. Alright, sorry.